Everybody, this is Taylor Sparks, Editor-in-Chief for Integrating Materials and Manufacturing Innovation, here with a brand new paper. This one is all about how you weld superalloys and how you can optimize that process. This work comes to us from researchers at IIT Dhambad, at ISRO, and at IIT Madras. So the actual alloy they're interested in is a nickel superalloy, this XH67MbTIO alloy, right? It's amazing. They use it in lots of aerospace applications, but if you're going to use it, then you're going to have to weld pieces together. And during that process, there can be things happening that we don't like. For example, they dive into it. They say that this is often used in semi-cryogenic engines for space launch vehicles. The alloy itself is made up of nickel plus things like chromium, molybdenum, titanium, aluminum. And the way that it achieves its strengthening is through the formation of these precipitates, these gamma prime precipitates, as well as carbides. Okay, that's all fine, except when you go to process this, for example, through welding, you can get segregation of these alloying elements that could lead to low melting point phases, intermetallics, things that are going to cause it to fail, right? There's also the possibility of cracking. So other people in the literature have tried to figure out how we can model this process to improve it. There's a couple important prior art papers they point out. For example, this paper in the Journal of Manufacturing Processes, where they applied this sort of IMMI method to TWIP steel. And that's exactly what they're going to try and do here. They're going to try and take this integrated micro and macro scale simulation under the conditions of welding, so gas tungsten arc welding. They're going to try and simulate both the heat and the stress impacts using finite element and the phase field method, and then use those results to guide welding process optimization. One of the things I like about this paper is that, yes, it's the IMMI method, but it's paired with real experiments. So here you see a diagram of an actual XH67MbTIO alloy, and they've done a weld on it, and they've labeled the different regions showing different thermal cycling. They've got a cross-section showing you what the cross-section actually looks like. If you were to zoom in on that, by the way, zooming in, you can actually see both the fusion zone as well as the heat-affected zone, and clearly these have different microstructures if you look at the experiment. So the question is, can we reproduce these using finite element and this phase field modeling? Well, the macro scale simulations using finite element look pretty good. It looks like we can actually simulate these same regions pretty effectively, matching the experiment and simulation pretty well. And if you have a good idea of what the temperature profile looks like through the material, both in the simulation compared to the real material, then you can use that temperature profile to calculate out what the distribution of different elements can be. And then you could actually compare that with the experimentally observed EDS maps, which are clearly showing in some cases elemental segregation. Once you have a model that you're sort of comfortable with, now you can actually explore how the different cooling rates possible during welding could lead to different segregation rates, right? Here it's showing you interdendritic segregation for titanium, molybdenum, chromium, and tungsten as a function of different cooling rate and associated temperature gradient. And that information allows us to construct these continuous cooling transformation diagrams like the one on the left here, where you can see as a function of different cooling rates, which phases are going to evolve. And obviously, if you know which phases are evolving, now you have control over this process so you can use it in an optimization loop, which is exactly what they've done. So I invite you to check it out, what I think is a really important and slick application of ICME with nice experimental validation, published in Integrating Materials and Manufacturing Innovation.